All right, ladies and gentlemen, welcome to Chapter 11, Molecular Shape and Bonding Theories, the very last chapter in Chemistry 1341. Here we go. It's all about the shape and bonding theories, how they relate to the shape. So here's the deal. Let's take a look at beryllium. And if you look at beryllium, it's sitting over there in group 2. It has 2 electrons in the 2s subshell. And what valence bond theory says is that if you're going to make a bond between 2 atoms, you need unpaired electrons in an orbital that will overlap to make those bonds. Now you can see that beryllium has 2s2 for its electron configuration in the valence shell. Valence shell is what are the electrons that do the bonding, but they're paired up. So according to valence bond theory, they can't make a bond. So we're going to tweak it. And the way we tweak it was with a theory called hybridization, which also came along through Linus Pauling. And we're going to promote one of these electrons in the 2s subshell to the 2p subshell, and then we're going to equalize their energies. Why in the world would we do this? Well, we're going to do this in order to make bonds. And if you remember from chapter 10, making bonds lowers the energy. So we pay an energy price to promote an electron to a 2p. Then we equalize the energy. The 2s comes up, the 2p comes down in energy, and so we have 2 unpaired electrons in beryllium, and so we have what we call the hybridization for beryllium, which is sp. It's a combination of an s orbital and a p orbital, and whenever we do that, and here we have the 1s and then the 2s electrons, they're being shared with the 2 hydrogens. What we have, as you've seen before, is a linear molecule. The electron geometry is linear, the molecular geometry is linear, and since the electron and molecular geometry are both linear, that means obviously we don't have any non-bonding pairs of electrons on beryllium, so both electron geometry and molecular geometry are the same. The bond angle is half of a 360-degree circle at 180 degrees. All right, let's keep going with this. Remember, valence bond theory says that you need orbitals that have they have unpaired electrons. Let me see if I can make that electron a little bit cleaner. Okay, they have unpaired electrons in 2 orbitals. They're going to overlap. They're going to overlap those orbitals to give you an electron pair, and that will form your bond. Okay. All right, hopefully, and anytime you have just 2 things, 2 electron domains around the central atom, the hybridization is sp. If you have a linear electron geometry, you have sp hybridization. All right, try and remember that. All right, so here we have a depiction of the shape of 2 sp hybridized orbitals. We've taken a 2s, combined it with a 2p subshell or 2p orbitals, and we mix them up. And this is the mixture of the s and p orbitals. And so what we wind up with are what we call hybrid orbitals, sp hybrid orbitals around the beryllium atom. Okay. Let's see what else we got here. All right, so this is just a little bit more of an explanation. You've got boron here, and you've got 2s2, 2p1. So this is the electron configuration for boron, 2s2, 2p1. It's atomic number 5. And we're going to hybridize that. So just like we did for beryllium, we're going to add some energy to one of the electrons that's in the 2s. So now we have unpaired electrons because this electron is gone. We have 2 unpaired electrons in the 2p, 1 unpaired electron in the 2s. Then we raise the energy, we hybridize, we lower the energy of the 2p, raise the energy of the 2s, pay a little bit of an energy price. Why would the atoms do that? Because now they can make 3 bonds. Boron can now make 3 bonds because it's got 3 unpaired electrons. And so what we have are 3 sp2 hybridized orbitals, each with unpaired electrons. They can make bonds, and so boron will make 3 bonds. The hybridization is sp2. Let's see if I've got a picture here. There they are. We've mixed 2s and 2 2p orbitals to come up with 3 absolutely equivalent sp2 hybridized orbitals, and boron loves to make 3 identical bonds. So if you have 3 electron domains, you have sp2 hybridized bonds. Now, this is not really difficult. 3 electron domains, sometimes we just call it 3 things. You have 1 plus 2 equals 3. Okay, so that's sp2 hybridization, and the geometry is trigonal planar. All right, let's see what else we got. All right, here is carbon. Helium is just the noble gas core for carbon. That's all that means. We're using core or abbreviated notation. You've got 2s2, 2p2. Now, we know that carbon loves to make 4 bonds, not 2 bonds. Based on valence bond theory, carbon should only be able to make 2 bonds. But if we promote one of these electrons to the 2p subshell, then raise the energy of the 2s, lower the energy of the 2p's, and we get 4 equivalent sp3 hybridized orbitals. They're absolutely equivalent to each other. And we know that carbon loves to make 4 bonds. Okay, it wants to make 4 bonds, and we have sp3 hybridization. If you have 4 electron domains, you have sp3 hybridization. It's not hard. 4 electron domains, 1 plus 3 is equal to 4. Okay, that's where we get the sp3 hybridization, from the 4 equivalent bonds. 1 plus 3 equals 4. I know that's an ugly 4. And here are the shapes of those bonds. So what do we have? We have a 2s. We have a couple of 2p's. We go ahead and we mix the 2s and actually 3 2p's, and we wind up with 4 sp3 hybridized orbitals. Okay, that is hybridization. Okay, let's do sp3d hybridized. This is for elements that break the octet rule, like phosphorus. We've got 2, 4, 6, 8, 10 electrons around the central atom. So that gives us sp3d hybridization. Let's take a look at it. 1, 2, 3, 4, 5 electron domains. They're all bonding domains in this particular case, but I want you to remember that hybridization is based on electron geometry, not molecular geometry. So here we go. So sp3 hybridization, let's count them up. 1 plus 3 is 4 plus 1, and that's 5 electron domains. That's an electron, I know. But at any rate, so here's what the shape looks like. We call this trigonal bipyramidal. You've got an axial region. So this is an axial domain, okay? And then you have 3 on the equator. So we would call this equatorial. I'm not even gonna, well, I guess I am trying. Equatorial domain, and that is around the equator of this particular geometry. Now, each of the representations that I have down here in stick figures represents trigonal bipyramidal because it's based on the number of electron domains. So I have 1, 2, 3, 4, let's include both those electrons, 4 and 5. That gives me trigonal bipyramidal electron geometry, 5 electron domains. You've got a series of 120-degree bond angles. You've got 90-degree bond angles. So here's the 90, and here is the 120 for the trigonal bipyramidal sp3 hybridized geometry, electron geometry. Now, over here, one of the non-bonding electrons, which occupies an equatorial position, is a non-bonding pair of electrons. You still have 1, 2, 3, 4 molecular domains or bonding domains, but you've got one non-bonding domain. So we call this geometry, this molecular geometry, seesaw, because it kind of looks like a seesaw. Oh, that is just so pathetic. But if you're working hard to try and read my handwriting, maybe you'll remember it. So this looks like a seesaw. I'll present that to you in class. If I have, let's say, 2 non-bonding pairs of electrons, I still have 1, 2, 3, 4, 5 electron domains. It's still sp3 dehybridized trigonal bipyramidal electron geometry, but the molecular geometry is in the shape of a T. So we call it T-shape. Okay? And one more. If I have 1, 2, 3, 4, 5 things around the central atom, 5 electron domains, I still have trigonal bipyramidal sp3 hybridized electron geometry, but my molecular geometry is linear if 3 of those domains are occupied by non-bonding electrons. They all sit in the equatorial region, and I'll try and clear that up for you a little bit. Okay, so here's the hybridization scheme. We're going to promote an electron up to the D subshell. Then we're going to equilibrate all of the orbitals, and so we'll have 5 equivalent sp3d hybridized orbitals. Okay, that's what we got. They're all sp3 hybridized. And you'll note that there are 4d orbitals that don't have any electrons in them. You just have these 5 hybridized orbitals, sp3d. 5 things around the central atom, sp3 hybridized. Okay. Oh, I missed one. Here we go. The last one we're going to deal with is sp3d2. And so here's what we're going to do. We're going to promote an electron from the 3p. This is sulfur. And then we're going to promote an electron from the 3s. So that's going to give us 6 unpaired electrons. They're all equivalent. Yes, we did bring the energy up for the 3s. We did bring the energy down for the 3d. We equilibrated the energy of all 6 of these orbitals. They're now sp3 hybridized. You probably can guess now. This is 1 plus 3 plus 2, which is equal to 6 domains or 6 orbitals. Each one of them are equivalent. They have an unpaired electron in them, which allows them to make a bond. So why would electrons do this? Well, because they get to lower the energy. It's all about energy. So by being able to make 6 bonds, they get to lower energy. Okay, energy comes down. More bonds means lower energy. All right, all the bond angles are 90-degree bond angles. 6 things, sp3d2. We call this octahedral electron geometry. Let's see if we've got any other examples in here. Okay, so valence shell electron pair repulsion theory simply says electrons, which are negatively charged, those in bonds, those electrons in bonds, those in non-bonding pairs, also known as lone pairs, can be thought of as charged. They have a negative charge. Let me try it one more time. That's a little better. They have negative charge. They repel each other because you know that negative charges, they repel each other. They try and push each other in the opposite direction. And what they're going to do is when you have these bonds and non-bonding electrons, they're going to push each other as far away as they can get until they run into another cloud of electrons. So for instance, if you have a linear molecule, no non-bonding electrons, it's pushed out to 180 degrees. Why is it pushed out to 180 degrees? Well, because down here underneath, they're doing exactly the same thing. So they repel each other until they get to a minimum amount of repulsion. If you have that's an sp hybridized. Remember, sp hybridized is linear. sp2 hybridized, trigonal planar. That's 3 things around the central atom. These will all repel each other, and they're going to repel each other until they equalize that repulsion, where there's no advantage to this bond being pushed this way because this bond is pushing this way, this bond is pushing this way. They all come out to an equivalent 120-degree bond angles. Now, here's the tetrahedral bond angle that I showed you before. And just to remind you, the trigonal planar, sp2 hybridized. Trigonal planar, sp2. Here's the tetrahedral hybridization. And what we have here is we have sp3 hybridization. 1 plus 3 is 4. There's 4 domains around the central atom, 4 electron domains. These happen to be all bonding domains. And when they push themselves out in this way, you get 109.5 degree bond angles. Okay, so tetrahedral electron geometry gives you 109.5 degree bond angles. Here is sp3d hybridized. That's the trigonal bipyramidal. That's got 5 electron domains around the central atom. You have 2 bond angles. You've got between the axial and equatorial, you've got a 90-degree bond angle. Between the equatorial region, you've got a 120-degree bond angle. Remember, you've got 5 things, 1s, 3 p's, and 1 d all add up to 5. That's 5 electron domains, trigonal bipyramidal. Electron geometry. And then finally, we've got octahedral electron geometry, 6 electron domains around the central atom, 1, 2, 3, 4, 5, 6. They're in a perfect 90-degree bond angle. There is absolutely no advantage for any particular bonding domain, and so they balance out at 90-degree bond angles. Kind of looks a little bit like a jack. Okay, that's sp3d2 octahedral. sp3d2 is the hybridization. 1 plus 3 is 4, plus 2 is 6. Okay, electron domain geometries is a function of number of electron domains. This just goes 2 through 6. So there's really only 5 hybridizations that you need to remember. 2 electron domains, sp hybridization. 3 electron domains, sp2 hybridization. 4 electron domains, sp3. And 5 electron domains, sp3d. And 6 electron domains, sp3d2. Well, even if you forget the geometries, all you have to do is look at the molecule and count the electron domains. 3 is sp2, and it's trigonal planar electron geometry. Notice that the hybridization is based on electron geometry, not the it's based on the electron geometry, not the molecular geometry. So electron geometry determines the hybridization. We count everything, whether it's a non-bonding pair of electrons or not. So if I had something that looked like this, okay, and I had there's a pair of electrons, there's a pair of electrons, all right? So there's 1, 2, 3, 4, those are bonding electrons. 5 electron domains means sp3, that's a p, believe it or not, 3d hybridization. 5 things, 1 plus 3 plus 1, 5. Okay, so 5 is trigonal bipyramidal, 120 and 90-degree bond angles, and sp3d hybridization. Okay? All right, so that's the key to figuring this stuff out, is count the electron domains. And then just know that all the hybridizations start with S, and the S is always a 1 domain. Okay, it's always 1. And then you just start adding the p's. If there's only one other bond, then or one other domain, then it's an sp hybridization. If there are 2 other domains, then it's sp2. If there are 3 other domains, it's sp3. You're out of p orbitals, so now you have to go to the d. So it's sp3d. That's 5 domains. sp3d2, that's 6 domains. Just count the domains. Molecular geometries, linear electron domain. So electron domain and molecular geometries for 2, 3, 4 electron domains around a central atom. So here you go. You got an electron domain geometry that is linear. 2 bonding domains, no non-bonding electrons, and so your molecular geometry is the same. In general, guys, if if you have no non-bonding electrons, so if non-bonding electrons is 0, then your electron geometry and your molecular geometry are the same. And just remember that the electron geometry determines the hybridization, but your molecular geometry can be quite different. So we have here 1, 2 electron domains, no non-bonding electrons around carbon. So we've got a linear electron geometry and also a linear molecular geometry. The hybridization is sp. Remember, if you have an electron geometry that's linear, you need 2 domains. So that's 1 plus 1, which is 2 domains. sp hybridized, linear electron geometry, linear molecular shape. Oh yeah, bond angle 180 degrees, half of a 360-degree circle. Trigonal planar electron domain. Here we go. 3 electron domains. And in this case, they're all bonding domains. So it's trigonal planar. So 3 bonding domains, no non-bonding electrons or no non-bonding domains. So automatically that means you've got a molecular geometry that is the same as the electron geometry, trigonal planar, like boron trifluoride here. 1, 2, 3. So that's going to be sp2 hybridization because you have 1, 2, 3. Remember, if it's sp2 and it's based on the electron geometry, it's 1 plus 2 equals 3. That's 3 electron domains. Now, what if you do have a non-bonding pair of electrons? So this is representing a non-bonding pair of electrons right here. They take up more space, but so we still have, so this is like nitrogen dioxide, or this is actually the nitrite anion, NO3 with a -1 charge. You'll notice that there's a resonance structure here, just as an aside, because you've got a double bond depicted here, but you remember from chapter 10 that that double bond is actually spread out over both of those oxygens. So you actually have 2 resonance structures. I could have put the double bond over here, and the truth is those pi electrons, those delocalized electrons, are spread out over both bonds. Both of these bonds are absolutely the same. All right, back to hybridization. This gives us a bent shape. We also call it angular, but bent is the more common term that we use. And so we have 1, 2, 3 electron domains. It's still sp2 hybridized. Remember, the hybridization depends on the number of electron domains, whether they're bonding domains or non-bonding domains. And you have 3, so it's sp2 hybridized, but the molecular geometry is different. And the reason it's different is because of this non-bonding pair of electrons. They take up a little bit more space and they kind of push these bonds down a little bit closer together than 120 degrees, but we won't worry about that. Okay, the bent geometry is less than 120, is about the limit of what I would ask you. This bond angle here is less than 120 degrees. And that's because the non-bonding electrons, they take up more space, they push a little bit harder on those bonding electrons. All right. Tetrahedral electron domain, that's 4 things. So here we're depicting 4 things around the central atom, 4 bonding domains, 1, 2, 3, 4. That automatically tells you tetrahedral electron geometry. Bonding domains are 4. No non-bonding electrons tells you that you've got a tetrahedral molecular geometry because no non-bonding electrons. That would be like something like CH4 or CCl4 or CBr4. Perfect tetrahedral molecule. Now, let's say I've got something like ammonia, where there are a non-bonding pair of electrons here. I still have tetrahedral sp3 hybridization because I have 1, 2, 3, 4 things. 1, 2, 3, 4 things around the central atom. That gives me tetrahedral electron geometry, but trigonal pyramidal, trigonal pyramidal. It kind of looks like a 3-sided pyramid because you got those non-bonding pair of electrons sitting up there, taking up some space, okay, pushing down on these bonding electrons, all right? It's still sp3 hybridized because it's dependent on the electron geometry, not the molecular geometry. Finally, look at a good old water molecule. Water molecule has an electron geometry that is tetrahedral because you have 1, 2, 3, 4 things around the central atom, 4 electron domains. That's what gives you your tetrahedral electron geometry. But 2 non-bonding pairs of electrons on the oxygen gives you this molecular geometry. You've got 2 non-bonding pairs on a 4-domain tetrahedral electron geometry. This gives you bent, and it gives you a less than 109.5 degree bond angle. It's more like 104.5, but I won't be that specific with the bond angles. The only bond angles you need to know are what we call the ideal bond angles, or at the very most, if there's a non-bonding pair of electrons, you can say slightly less than 109.5 degrees, and that will be acceptable. Okay? All right. Let's keep going. That's what a tetrahedral geometry looks like. Non-bonding pairs and the bond angle. Non-bonding pairs are physically larger than bonding pairs, therefore their repulsion are greater, which tends to compress the bond angles. So here is a perfect tetrahedral molecule, CH4, that's methane. You've got 4 bonds to carbon, and you have equal repulsion between all of those bonds for a perfect 109.5. Here's ammonia. Now, ammonia, you know that non-bonding electrons, they take up more space, so they're going to push a little bit harder, and they're going to squeeze these bonds down to 107. But all I would ask you is, what are the bond angles on ammonia? And you would say slightly less than 109. Oh man, that's so ugly. Yeah, slightly less than 109.5. The real bond angle is 107. For water, you've got 2 non-bonding electrons. They're really pushing down here, and they're pushing on each other as well, but they're also pushing down here, and they reduce the bond angle to 104.5. Still, if I ask you for the bond angles for water, all you would have to say is either 109.5 or slightly less than 109.5. That would be a better answer. Okay? All right, trigonal bipyramidal. This is the most complicated geometry that there is. You have sp3 dehybridized molecules. Why? Because you have 5 electron domains, 1s, 3p, 1d, that equals 5. Trigonal bipyramidal electron geometry. The molecular shapes that you get out of it, let's say you have PCl5, so that's a perfect trigonal bipyramidal electron and molecular geometry. However, if one of the electron domains is a non-bonding electron domain, I prefer drawing it like this because this is more recognizable. If you were ever a kid in the playground, this looks like a seesaw, and that's because there's one non-bonding pair of electrons in the seesaw trigonal bipyramidal electron geometry. And so that gives you a molecular geometry that is seesaw. And then we have this, which again, the non-bonding electrons go in the equatorial position, and that gives us a T-shape molecule. One more, if you have 3 non-bonding electrons, this is something like xenon difluoride. You've got 1, 2, 3 non-bonding pairs of electrons. Let me see if I can do a little better than that. No guarantees. So it would look like this. You've got fluorine out here, fluorine out here, and you've got xenon sitting in the middle. I know it's a noble gas, but you've got 3 non-bonding pairs of electrons here, here, and here. And so you still have 1, 2, 3, 4, 5 electron domains. So you still have trigonal bipyramidal electron geometry, but you have a linear molecular geometry. Okay. All right. So there we go. That's pretty ugly. But anyway, this is representing the axial region. That's axial. Okay, just like the axes of the Earth. And then around the perimeter, around the equator, that's the equatorial region. And they have 120-degree bond angles between them. All right. Last one, octahedral electron domain, sp3d2 hybridized. We've talked about that. You have 6 things around the central atom. If they are perfect, so let's say SF6, that gives you sulfur hexafluoride, that gives you a perfect octahedral electron and molecular geometry because you don't have any non-bonding electrons. If we put one non-bonding pair of electrons on the central atom, doesn't matter where they go because all the domains are the same, they'll first go into any one of those locations, and they produce a molecular geometry which we call square pyramidal. You can kind of see the square there, and then they all go up to the point of the pyramid. And down here below, you've got the non-bonding pair of electrons. Now, if we have 2 non-bonding pairs, this is the last one, they're going to be as far away from each other as they can, because remember, non-bonding electrons take up more space. So they don't want to be at 90-degree angles to each other. That is forbidden. They will be at 180-degree bond angles, but what you have left is square planar molecular geometry. So this is square planar. Okay? 2 non-bonding pairs of electrons on an octahedral geometry. Okay, so there is what the octahedral geometric shape looks like. Okay, let's talk about sigma and pi bonds. So how atoms form single, double, and triple bonds. I'm going to show you some shapes, how they form bonds, and then we're just going to talk about sigma and pi bonds. Now, anytime you have two nuclei that are lined up with each other, and that would include something like, let's say H2, okay? You have this single bond here. That's what we call a sigma bond, or carbon-carbon single bond is a sigma bond. It's along the internuclear axis. It's lined up straight across like that. Now, if I have a double bond, I do have a sigma bond, but I also have a pi bond. So you take p orbitals, and those p orbitals will sit above and below the internuclear axis, really ugly, above and below the internuclear axis, and they're sharing electron density above and below. The important thing to remember here for answering questions is that pi bonds, that double bonds have one sigma and one pi bond. So a double bond is one sigma and one pi bond. A triple bond is one sigma and two pi bonds. Okay, so keep this in mind. If I give you a complicated molecule, just go through it, and I ask you for the sigma and pi bonds, go through it, count every single single bond, and those are all sigma. Go count all the double bonds or triple bonds, add sigma bonds for each of those to the tally, and then a double bond also has a pi bond. A triple bond has two pi bonds. So all bonds have a sigma bond. A double bond has one sigma and one pi. A triple bond has one sigma and two pi. Remember that. Okay, I'll test you on it later. So let's just go ahead and look at all of this and see what we can tell. So the first thing I'm going to do is I'm going to figure out the geometry and the hybridization, and then the sigma bonds and the pi bonds. So first of all, 1, 2, 3, 4 single bonds around carbon. So that means that this carbon is tetrahedral. It has tetrahedral electron geometry. There are no non-bonding electrons, so the molecular geometry around this number 1 carbon is also tetrahedral, and that means its hybridization is sp3, and its bond angle is 109.5 degrees. And then over here, this carbon looks exactly like the carbon on the left. So number 2 carbon looks exactly the same. 1, 2, 3, 4 things around the central atom. Tetrahedral electron geometry, no non-bonding electrons, tetrahedral molecular geometry. The tetrahedral electron geometry tells me it's sp3 hybridized and that the bond angle is 109.5 degrees. Let's count the sigma and pi bonds. I'm going to just count bonds. Let me erase a few things, okay, just to make it a little bit cleaner. Okay, here we go. All right, 1, 2, 3, 4, 5, 6, 7 single bonds, no double bonds, no triple bonds. That means that the total is 7 sigma bonds. All right. And that is pretty much it on that one. All right. Oh, and this is what it looks like. You do have sp3 hybridization. And so the sigma bond is a hybridized sp3 bond going right through here. You have an sp3 bond going up here, and it's overlapping a 1s orbital with each of these hydrogens here. Okay, so these are all around carbon sp3 hybridized orbitals. Okay, so here is ethene, C2H4. Here's the Lewis structure. And let's first of all determine the electron geometry. 1, 2, three things around the carbon number 1. That means we have a trigonal planar electron geometry, no non-bonding electrons, so the molecular geometry around the leftmost carbon is also trigonal planar, and the hybridization is sp2, and the bond angles 120 degrees. Just take a 360-degree circle, split it up into 3 pieces of pie. The number 2 carbon looks exactly the same. 3 things: trigonal planar, electron geometry, and molecular geometry, sp2 hybridized. Okay, and so here we have the hybridization. We take a 2s electron, we promote it, equilibrate the energies, and we get 3 sp2 hybridized orbitals. Here's what she looks like up here. There's your hybridized orbitals for the trigonal planar. Okay. Okay, and here you go. You've got your sp2 hybridized orbitals, and then you have this p orbital sticking above it where you have your double bond. Let's go ahead, count up the sigma and pi bonds. I have 1, 2, 3, 4, 5 sigma and 1 pi bond. So just count every single bond. That gives you the sigma. 1, 2, 3, 4, 5. That gives you your sigma bonds, 5 sigma. And then the double bond gives you your 1 pi bond. Okay. And so this is how we depict this particular molecule. You've got those p orbitals, which are sharing electrons above and below. This is the double bond. So both of these lobes above and below is actually the pi bond. All right. These are the sigma bonds, and that's a sigma bond from one carbon to another and from the hydrogens to the carbon. Okay. So 5 sigma, 1 pi bond. This is, as you can see, it says here 1 pi bond. And then finally, ethine, which is also known as acetylene, which is used in cutting torches in metalwork. And so here we have 1, 2, 3, well, around each carbon we have 2 things. So the hybridization is sp because it's a linear geometry between this bond, and then the triple bond between the 2 carbons and right here. So let's take a look at this. So we've got a 180-degree bond angle. We've got linear electron and molecular geometry. There's no non-bonding electrons. I have 1, 2, 3 sigma bonds, but it's a triple bond, so I get 2 pi bonds out of the triple bonds. And I think you're going to be able to see what that looks like right here. There's a pi bond here on one axis and a second pi bond on another axis. Okay, so you have 2 pi bonds which create the triple bonds. Okay, all right. All right, so double bonds. Here you have sp2 hybridized orbitals. You have unhybridized 2p, 2pz. They form the carbon-carbon and carbon-hydrogen sigma bonds. And then over here you have carbon-hydrogen sigma, carbon-hydrogen sigma, carbon-carbon sigma, and then the 2p orbitals that are unhybridized, they form the carbon-carbon double bond, okay, or pi bond. So double bond, 1 pi bond, 1 sigma, okay. Triple bonds, here we go. We've got unhybridized 2p, 2pz. You've got the hybridized sp bond. Same thing with hydrogen over here. So you've got a carbon-hydrogen sigma, carbon-hydrogen sigma, carbon-carbon sigma, and then you have two pi bonds that are at different angles to each other, okay, such as PZ and PX or PY. Okay, so that is sigma and pi bonds. Honestly, if you just count, okay, and here's the deal. Every single bond is 1 sigma. Every double bond is 1 sigma, 1 pi. Every triple bond is 1 sigma and 2 pi bonds. Pretty much all you need to know. All right, let's take a look at this guy. Okay, so here we've got 1, 2, 3, 4 things around each of the outside carbons. That's sp3 hybridization, tetrahedral electron and molecular geometry, no non-bonding pairs of electrons, 109.5 degree bond angle. But around this carbon, you have 1, 2, 3 things around the central atom. That's trigonal planar electron geometry. There's no non-bonding electrons. sp2 hybridization. So sp3 here, sp3 on the outside over here, and then sp2 around the centermost carbon on 120 degree bond angles. Let's count up the sigma and pi. 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma. There's 1 double bond, so that gives us 1 pi. So I counted every single bond to get my 9 sigma, and then the 1 double bond gave me the 1 pi. Okay, this is what it looks like in model form. Okay. All right, let's count them up. Let's do our work. So I've got 1, 2, 3 things around this carbon. That makes it trigonal planar. sp2 hybridized, 120 degree bond angles. Around this carbon, 1, 2, 3 things. So it's also trigonal planar, sp2 hybridized, 120 degree bond angles. But around this carbon, I have 1, 2, 3, 4 things around the central atom. That's sp3 hybridized, tetrahedral electron geometry. Around this carbon, I've got 1, 2 electron domains. That is linear sp hybridization. Same thing around this one. That's 180 degree bond angle. Let's count up the sigma and pi. So first of all, my technique is to count everything to get my sigmas. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma. I have a triple bond here, which gives me 2 pi bonds. I have a double bond here, which gives me 1 more pi bond for a total of 3 pi bonds. So 10 sigma, 3 pi. That might be your question. That's what it looks like. Polarity of molecules. So when you have a geometry where polar bonds cannot cancel each other, then you have a polar molecule. So our first rule is that generally speaking, to get a polar molecule, you need polar bonds. I can show you some exceptions to that, or at least one exception, but let's start with polar bonds. Now, the carbon-oxygen bond is a polar bond. Oxygen, an electronegativity of 3.5, carbon at 2.5. That is sufficiently polar or difference in electronegativity to say this is a polar bond and this is a polar bond. But notice, you have two things around the central atom. Doesn't matter that it's a double bond. You have two electron domains, and so you have a linear geometry, and this polar bond, which has a negative charge out here, and this polar bond, which has a negative charge out here, they are canceling each other, so that overall this molecule is non-polar. So we're looking for a geometry where polar bonds cancel if we're looking for a non-polar molecule. On the other hand, we're looking for a geometry where the polar bonds cannot cancel if we need to find, if we're trying to determine if it's a polar molecule. Water is such a molecule. You have oxygen with a 3.5, and I want you to remember there are two non-bonding pairs of electrons up here. The reason this molecule is bent is because of those non-bonding pairs of electrons. Remember, valence shell electron pair repulsion theory, VSEPR theory, says that electron domains will repel each other. So these non-bonding electrons are pushing the bonding electrons out of the plane, and so what you have is a bent molecule. This bent molecule with these very polar bonds is a polar molecule because the polar bonds can't possibly cancel when they're at an angle like that. They're actually adding to each other like that. That is a polar molecule. Water, if you don't get anything else out of the course, remember that water is a polar molecule. In general, bent molecules will be polar. They should have polar bonds, but bent molecules are polar. So dipole moments and molecular polarity, linear molecules, if the bonds are the same polarity, they'll cancel each other and it'll be non-polar. Bent molecules are almost always polar. Tetrahedral molecules can be nonpolar, but if you have something like, let's say, let's do nitrogen here and hydrogen. So here is ammonia, or a really terrible facsimile of ammonia. Remember, there's a non-bonding pair of electrons up here on the nitrogen. Now, this is a tetrahedral electron pair geometry. You have 1, 2, 3, and 4 things around the central atom. It's sp3 hybridized. It is a tetrahedral molecule, okay? But these polar bonds here cannot cancel each other. They can't cancel each other because they're in this trigonal pyramidal geometry, just similar to a bent geometry. There's just a third leg down here. And so in this geometry, the polar bonds can't cancel, and so this molecule would be polar. Ammonia is a polar molecule. Okay, trigonal pyramidal, which is what we just had, that's going to be polar. I'll give you some other clues. T-shape with polar bonds is polar. Seesaw with polar bonds is polar. Square pyramidal, which you get from octahedral geometry, that's going to be polar. Any asymmetrical shape where the dipole moments cannot cancel will be a polar molecule. So, determining whether a molecule is polar or not. Are any of the bonds polar? Yes. Are the atoms symmetrically distributed around the central atom? If the answer is yes, are all outside atoms the same? If the answer is yes, it's a non-polar molecule, because all the polar bonds cancel each other. If the atoms are not symmetrically distributed, the molecule is polar with polar bonds. Okay, so remember, bonds, you need to have at least one polar bond in there, all right? So if there's not, the molecule is nonpolar. Okay. Now I do have an exception up here, which is ozone. So that's the way you tell whether a molecule is polar or not. Now let's look at ozone. Ozone is a bent molecule. You have an oxygen here in the center. You have an oxygen on either side. Now you might remember that that this is a resonance structure. This double bond could have been put over here as opposed to over here. These two bonds are exactly the same, or the average of both resonance structures. But here's the deal. This poor oxygen, which is very electronegative, is having to share electrons not with one oxygen, but with two. So both of these external oxygens are pulling electron density away from the central oxygen, which is creating polarity in this bond. So that's actually making the bond polar, and it's a bent molecule. It's trigonal planar electron geometry, but bent molecular geometry. And so with the two oxygen, it makes the bonds polar, and the bonds can't cancel each other. So this is a polar molecule. Okay, summing it all up, if it's symmetric, linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, square, planar, that is symmetric. Non-symmetric, bent, trigonal pyramidal, seesaw, T-shaped, square pyramidal. These are the molecular geometries that tend to be polar molecules. Polar bonds and bent, trigonal pyramidal, seesaw, T-shaped, square pyramidal, these guys are going to be polar. Okay? Symmetrical, it's a little bit harder to tell sometimes, but tend to be non-polar if all the atoms are the same. Okay? All right. I think that's just about it. Polarity of molecules. For a molecule to be polar, it needs to have polar bonds, electronegativity difference, that's theory. It needs to have an electronegativity difference, bond dipole moments measured, have an unsymmetric shape, that is angular, bent, trigonal pyramidal, seesaw, T-shape, square pyramidal, those asymmetrical geometries. Those unsymmetrical shapes lead to polar molecules. Polarity affects the intermolecular forces of attraction, like boiling point, solubility. We say like dissolves like. Non-bonding electrons pairs affect molecular polarity by changing the shape of the molecule. That's how they do it. Like the non-bonding electrons in water, which make it a bent molecule, and water is a polar molecule. Same thing for ammonia. You've got a trigonal pyramidal, you've got a non-bonding pair of electrons up here pushing these down out of the plane. Okay? All right, ladies and gents, I think that's it.